Good afternoon. In this video, I'm going to work through the first 19 problems of the practice test for Chapter 4. And this is going to cover part 1 of our Chapter 4 test. So in these first few couple problems, we're just looking at rewriting a log as an exponential. So remember, your base is the base of the log. So this is going to be 2 to the power of y equals 10,024. So you don't need to solve it, you just need to rewrite it. All right, so in this next one, your base is 4, your exponent is x, and that will equal y. And that is all you have to do. Let's go the other way. So in number 3, if it's a base of e, we usually use natural log. So the ln of 30 is going to equal k. Now, if you forget that the natural log is a base of e, you could certainly write this as log base e of 30 equals k. So these are both correct. We usually just use this one. All right, and then in number 4, we're going to write the log base 5 of 125 is equal to 3. All right, so in 5 and 6, then we are going to expand each expression. And when we do that, we need to make sure we eliminate all products, quotients, powers, and roots. So in number 5, the first thing I notice is that these two pieces are being multiplied. So when I expand them into two logs, it will be log base 2 of x cubed plus log base 2 of y to the power of 6. Then you can take those exponents and put them to the front. So our final answer is going to be 3 log base 2 of x plus 6 times log base 2 of y. So notice in that problem, we don't have any more products, we don't have any quotients, we don't have any powers, and we certainly don't have any roots. All right, let's try that with number 6. So this is a natural log, but the rules are still the same. So first we will break up this quotient with subtraction. All right, so that will give us the natural log of AB minus the natural log of the cubed root of c. Oops, not the cubed root of 3, cubed root of c. And then we can do one more thing in this first log that can be broken up with addition because that is a product of a and b. So when we split that up, it will be log of a plus the natural log of b. And then here we're going to do something with this second piece. I'm going to write this as minus the ln of c to the power of 1/3. So if you take the cubed root, remember that's the same as a 1/3 power, because then we can take that 1/3 and put it to the front. So our final answer is going to be the natural log of a plus the natural log of b minus 1/3 the natural log of c. So now I don't have any more products, quotients, powers, or roots in that problem. All right, in 7 and 8, we're going to go backwards. Now we're starting with an expanded expression, and we're going to condense it. The first thing you always do is restore your exponents. So this 2 is going to go back on as a power, and this 4 is going to go back on as a power. This will be log of 8 squared minus log of 2 to the power of 4. Now this is subtraction, so when we condense it, it's going to be a fraction. So log of 8 squared over 2 to the 4th. And then since those are just numbers, we can simplify this. So we have log of 64 over 16, and 64 divided by 16 is 4. So this is just the log of 4. All right, so if we have variables, well then we're not going to be able to make just log of a number. So again, first thing you always do is put your exponents back on. So this is the natural log of 5 plus the natural log of x squared minus the natural log of the quantity x plus 1 cubed. Now at this point I usually just say, okay, let's make one big log, and since there's subtraction, I know I'm going to have a fraction. The pieces that go on the top are 5 and x squared because those are positive terms. So these pieces will go to the numerator. And then the x plus 1 cubed goes in the bottom because that's being subtracted. All right, and that is actually your answer. We're done. Okay, these next 3 we're going to do without a calculator. So in number 9, I actually just write this as equal to x, and then I change form. So I'm thinking 7 to what power gives me 1? Well, I know the only way to make that true is if x equals 0, so this answer is just 0. In number 10, this is one of our properties of logs. That base is the same as that base. And if that is the case, your answer is just your exponent. So you don't really need to show any work there if you remember that rule. And it works whether that log is like it is in number 10 or if it's in the exponent like it is here. This base of 12 matches the log's base of 12. So since those are the same, your answer is just x. So again, there's no work to show here. That's just using those special properties. All right, 12 and 13, we're going to use that change of base formula. And even if you do have a TI-84, which can take logs of bases other than 10 or e, I still want you to know this formula. So you can write this as log of 25 divided by log of 7. And just make sure when you do this in your calculator, you make sure that parenthesis right here is closed before you divide by the log of 7. So this to 4 decimal places is going to be approximately 1.6542. Okay, let's try that again. So we're going to do the log of 0.0034 divided by the log of 17. And that to 4 decimal places is approximately negative 2.0062. All right. So the last few problems on this page are some word problems. For 14, they want us to find the growth rate of this population. So we have a bacteria can grow from 1,000 cells to 8,000 cells in 5 hours. So I'm noticing that this is exponential growth, which means we're going to use this formula, that n of t is equal to n naught e to the power of rt. So if we're looking for the growth rate, that means we're trying to find r. We know that this 8,000 is our current population. The 1,000 is our n naught, that was our initial, and 5 hours is our time. So let's plug in what we know. We have 8,000 equals 1,000 e to the power of r times 5. So the only thing I don't know is r, which means I can solve. So to solve this, we'll first isolate the e part, the exponential part. So we need to divide by 1,000. So we end up with 8 equals e to the 5r. So now at this point, we can change it into a log. So this is the ln, since it's a base of e, so the natural log of 8 is equal to 5r. And since I'm trying to solve for r, I would divide by 5 before I get my calculator out. And again, when you're doing this in a calculator, make sure you close up that parenthesis before you divide by 5. So if you plug this in your calculator, you get 0.4159 as your r, which would mean our growth rate is about 41.59%. All right, so it's growing pretty quickly. 15 wants us to use that to answer the question, what will the population be after 1 day? Well, remember they gave us time in hours, which means when we use our formula, we need to use hours. So we're going to use 24 hours instead of 1 day. All right, so we're trying to find n of 24, which is going to be the initial 1,000 times e to the power of 0.4159 times time, which is 24. And you'll just go ahead and plug that right into your calculator. And this is going to be an approximation, but when you do this, you should get something in the ballpark of 21,620,000 bacteria cells. So it is a pretty high number, but again, that's because that growth rate is so high. All right, so let's do one more growth rate problem. We have the number of freshwater drum sheep's head in the upper Mississippi River is modeled by this function. N of t equals 12e to the power of 0.012t, where t is measured in years, and n of t, so the population, is measured in millions. Okay, so for example, what that means is this is like 12 million fish. It's not 12 fish. And that is actually our answer to number 16. What is the initial estimated of the fish's population for this model? So I think that's a typo. Just say the initial estimate. So in other words, how many fish are there to begin with? And that's that N naught, which is 12 million fish. All right, and that's all you have to do for number 16. Number 17 is, what is the relative growth rate? Well, if you know that basic formula, that's this. That's R. So 0.012 is your R, which it's a lot of times we'll express that as a percent. So this is 1.2%. That's it. And then in 18, it wants us to figure out what will be the estimated freshwater drum population in the upper Mississippi River after 6 years. All right, so they're giving us time. And since they told us t was in years in the problem, we can just use 6. We don't have to do anything with that. So we're finding n of 6. All right, so if we take 12 times e to the power of 0.012 times 6, your calculator will give you approximately 12.895864. But remember, that's in millions. You don't have 12.89 fish. You have 12,895,864 fish. Okay, so it makes more sense to rewrite your answer in millions. Okay, and then lastly in 19, it says if this model started on January 1st, 1980, when, year and month, will the population reach 19,600,000? Okay, so first thing I'm going to do is write that as 19.6. Because that's the number of millions I have, so that's what I have to use for in my equation is just 19.6. All right, and then I'm trying to find the time, okay, which means I'm solving for t. So we'll say 19.6 equals 12 e to the 0.012t. All right, so first we need to isolate the exponential by dividing by 12. So if you do that, you get 1.63333, so it's repeating. And that equals your e to the power of 0.012 t. Now we can turn it into a log, so the ln, or the natural log, of 1.63333 is equal to 0.012 t. And then let's divide by that 0.012. 0.012. And if you do that, you'll get about 40.9. So that tells you how many years after January 1st, 1980. So we know this is going to happen in 2020. And how you can figure out what month is you can take 0.9. So I'm going to grab a calculator here. Where is my calculator? I don't know. Oh, never mind. It's in here, isn't it? I don't know where the calculator is on an iPad. This is fun. All right, you know what? I can't find it. Anyway, so to figure out what month this is, you take the decimal part, which is about 0.9, and you multiply it by 12 months. And that's going to give you 10 something, like 10 point whatever, which means this is in October. So it would be October. And since it's 40 years after 1980, it's going to happen, or it did happen, in the year 2020. All right, so that's part 1. Let me know if you have any questions, and we will see you next time.